All right, we're starting Chapter 6 in Precalculus 30. Chapter 6 is a bit more abstract than some of the other chapters. We talk about trigonometry again, but we're talking specifically about identities, trigonometric identities. So we know that periodic functions or periodic situations in life can be represented by sinusoidal functions. That's functions that look like a sine graph, right? So sine or cosine. What we're going to be focusing on here are identities. So I want you to focus here on this section, or this sentence right here. In this chapter, you will explore equivalent trigonometric expressions. That's the key right there. Equivalent trig expressions. So, trigonometric expressions that are equal to each other in every respect for all possible values of the variable that's in them. For all the angles that we could ever consider, all the x values, the whole domain. Okay, so that's the focus right there. If we look at your textbook here, okay, I'm looking at these pictures and I'm thinking about identity. All right, this section, chapters, talks about identities. Now, you, as a teenager, will have an identity. Where do you find your identity? Are you a horse jumper? I'm not sure if we have any horse jumpers here. Are you a track star, a javelin pro? Look at this girl here, Elizabeth Gleedle, I want to say. I'm not sure if that's right. But anyways, she's from Vancouver. She holds the Canadian women's javelin record, apparently, as of 2009 anyway. So that's pretty cool. I used to throw javelin in high school as well. Did the throwing events and the sprinting stuff. You'd never guess now. But I like the javelin. Maybe you're a basketball player. All right, we have lots of basketball players in this school, right? Maybe you're a basketball player. Maybe you're a tennis player. Again, track star, whatever. You know. Anyways, so when we talk about identities, and we'll go flip back to the notes here. When we talk about trigonometric identities, an identity is what is always true about someone or something. So if we talk about you and what is your identity, maybe you identify with some of those people in the pictures there. Maybe you're a musician. There wasn't a musician represented. There's lots of things that weren't represented there. But some people identify with those things. Now, what I want to ask you is being a basketball player or a track star or a mathematician or a whatever, is that your identity? Is that who you truly are all the time? Is that who you are for your entire life in every situation? Okay, these are questions that you need to ask yourself. Because there are many, a former professional athlete that are struggling deeply with their identities after their careers. So you think about it. The most famous sports person you can think of, if they were a star and that was their complete identity throughout their entire career, but when their career is over, they're no longer that star. They're no longer that top-tier player, and they have to find another purpose. That is not their true identity, right? And we're in a Christian school environment here. And so I would hope that for you, just like it is for me, that your true identity, like who you are all the time for your whole life, in every situation, is you are a child of God, right? That you are a Christian. That you know where your true identity comes from. And you know what? It doesn't matter if you're a basketball star now. You will always be a child of God. It doesn't matter if you're good at school now. You hit university, you may find that you're not as good at school. I don't know. Marks drop in university. You may be a boyfriend or a girlfriend, or maybe you think you're pretty hot stuff right now. Well, you know what? You end up looking like me 20 years down the road, okay? Look at me, all right? Okay? This is what you might end up looking like. So that may not be a good thing to cling to right now, because that changes a bit. Oh, I didn't think I was hot stuff. No, but you can look at some of my grad pictures up there, and you can make judgments for yourself. Yeah, that's right. Check out the mullet there, okay? There's some pretty cool hair. I had a lot of hair back then. I don't know if you guys can. Yeah, you can look at that later. Anyways, I was a hockey player, right? That was my identity. I was a hockey player, and everybody knew me as a hockey player. I got a scholarship. I went down to the States. I was on the campus of Cornell University. And I would say something to people, anything, like, hey, how you doing? They would laugh at me. You must be a hockey player. What? How did you know that? Well, you're Canadian, eh? I could tell by the way you talk to me. And literally, I'm like, no, listen, you guys are all the ones with the crazy accents here. I talk normal. You sound really crazy. And they would like make fun of me, like, oh, about, look at the roof. And then, they all these different words, they were from Manhattan, they had Boston accents, and they didn't say their I's very well, and I did, and so I was weird. That was my identity. But that's not my identity anymore. I'm not a hockey player anymore. Yeah, I can't even fake the accent, but it was really, really weird. They could tell who I was and what I was doing there because I just said hello to them. They're like, oh, you must be a hockey player. So anyways, that was sort of my identity there. Now I realized as I grew older that I'm not the hockey player anymore, and now I'm a father, now I'm a husband, now I'm a teacher. So is that my identity? What I'm getting at here, okay, that's a big ramble. What I'm getting at here is that in math, okay, an identity is a truth statement that is true for any permissible value in the statement, okay? So I hesitate to use the word equation. I'm not using equation here. I'm using mathematical statement. So what I want to ask you, for example, is this statement an identity? That means, is this statement, true for any possible value for x that I put in there? You would, of course, say no, right? Is there a value or values that this is true for? Yes, if we had x equals 2. That looks pretty good. 2 squared, you would probably agree it is 4. It would also work for negative 2. That's 4, sure. But what about 3? That is not 4, so this is not a mathematical identity. Okay, it's not. It's not true for any value of x. Compare that to this. What about this one right here? Okay, now this is getting a little bit closer, isn't it? To what I mean by a mathematical identity. If you take any value, any value for x that you could possibly think of, and you take the square root of it, and then you square that answer, will you get x back? Now, you could probably think of a lot of examples, right? And you would think, okay, any example I think of would be true. Is there a non-example? Is there a counterexample? Because that's one way to prove or to disprove something. You can disprove a claim that this is an identity by finding one counterexample. A negative, okay? So what about a negative? That's very good. What if you have a negative x? Oh, like a negative 4, and you take the square root of it, and you square it. Whoa. Does that give, that is unreal. Someone's, okay, very good. Oh, what, is this, so is it true? Why don't you test that? Get on your calculator, test it. Is it true? What does your calculator think about that? I don't know, what do you think? So you're going to run into a problem probably if you do this, right? The first step here. You're going to run into a problem, right? Okay, what about this? Now, this is sort of grade 10 stuff, and I know you guys know this, but you knew that x to the power of m over n can be written as the nth root of x all to the power of m, or it can also be written as the nth root of x to the power of m underneath there. So if you did this a different way on your calculator, and you did this, would you get negative 4? Okay, well, if you square negative 4, what do you get? Okay, you can't square root a negative, but if you square the negative 4 first, what do you get? Positive or negative? Oh, you get positive. So can you take a square root of a positive 16? Okay. But it's not going to be negative 4. Okay. So, there you go. You see how you're testing this stuff out? So is this a mathematical identity, would you say? Okay, well, we found some counterexamples there. Now, this is sort of what we're going to be delving into, okay? Now, you're not going to have to test every possible value, okay? But this is the kind of thinking that I want you to think about, okay? So we've found some counterexamples that this is not a mathematical identity. I would think that's great. Okay, what about this one? Is this true all the time? Sure? Okay, what is x and y and what is r? Is there a context you're saying sure for? Like, what is r? How do you decide what the variables are? How do you decide what r is? Okay, what is this for? Where have you seen this? Okay, Pythagoras' theorem, okay. Yeah, R, what is the R all about? Remember what we just did? Think about the unit circle here, okay? If you're thinking about the unit circle and you set R equals to 1, then I would maybe say, yeah, okay, then this is good for the unit circle, right? We're getting closer. But think about that unit circle. So draw this, write this down. Here's the circle, here's the origin, here's a radius of 1. And integrating this whole idea of this equation right here, let me just gather that up for us. Let's copy that, paste it right there. Pink 1 there. Okay, you think about this. Didn't we say that any point that's on the unit circle should satisfy this equation? So didn't we really say that if we square any x value that's on the point and we add that to the square of any y value that's on the point here, that we should get 1? Okay, so, sorry? Yeah, it has to be on the unit circle, right? That's what we said, yeah. If it's on the unit circle, it will satisfy this, right? Okay. So this is always true for any x and y values that are on the unit circle. Okay? True for any of them. So we're getting close to an identity here. On the unit circle, what is x and what is y? X is cos theta, right? The first, yeah, okay, cos theta, and y is sine theta. So for any values on the unit circle, we know that this is true. But what about if I substitute cos and sine in? Does that make sense? So cos squared theta plus sine squared theta equals 1. Now notice I put the squared here, not the squared at the end. We talked about that, I think, before. So is this true for any value on the unit circle? You're thinking about it, you're thinking maybe yes. Okay? Now, what about if we're talking about just cos and just sine now? So what I'm saying is that cos of an angle, any angle, okay, we're not talking about points in the unit circle anymore, we're talking about any angle, any theta, any angle, right? Any of these, anything. If you do this, and you do this, and you add them together, does it equal 1? I want you to take a few minutes right now, and I want you to test different angles and test this expression, this equation, to see if it's true for any value that you choose. Make sure your calculator's in radians if you're using radians, or degrees if you're using degrees, I guess. Okay, go ahead and take a minute to do that. Okay, so many of you you're working on your calculators there. I'll show you what I've done on my calculator, and I've done a few here. You can't even see this on the screen, but I tried sine of 25, and I got my calculator in degrees here, okay? I tried sine of 25 squared plus cos of 25 squared. I got 1. I tried 75, got 1. Tried negative 75, got 1. What about you guys? Is this working for you with any angles that you try? And they have to be, of course, the same angle. This is theta, this is theta. It's got to be the same angle. Is anyone getting any other than 1? Okay, so it seems like everything that we've tried, 1. Now let's take a look at this algebraically. You know that you have your memorized special triangles. And so let's say the cos of, let's take 60, for example. So if we did the cos of 60 squared, and we added the sine of 60, and we squared that, what would we get? So let's just test that out. What's the cos of 60? That's adjacent over what? Adjacent over hypotenuse, okay? And what's the sine of 60? That's opposite over hypotenuse. Root 3 over 2. We'll square those. So this is 1/4. This is 3/4. Oops, not equals there. Plus, look at that. That equals 1. Okay, let's try something with a 45. Well, Sine of 45 is what? Let me write that down. Sine of 45 is opposite over hypotenuse. What is it? 1 over root 2 squared. And of course the cos is 1 over root 2 again. All right, so what does that equal? Well, that's 1 squared over root 2 squared is 1/2 plus 1/2, that's 1. Okay, so as far as our exploration here, it seems that everything that we've tried has worked. Okay, and we cannot find a counterexample at all. So this is ding 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 ding. This is an identity. That is an identity. It's called the Pythagorean identity. Okay, and I'm just going to make myself some space here so I can write that down. I didn't anticipate using this much space. All right. So before we get to those, let's write this out here. So the Pythagorean identity. Pythagorean. And that is this. And now it doesn't matter which one which way you write it. I think you'll see most of the time that they start with sine squared theta. But doesn't mean not. To some. But that's the Pythagorean identity. This is always true every time for every single value of theta. Any value of theta that you can think of. All right. That's number one. That's identity number one that we're going to learn here. Some other identities are called the reciprocal identities. That's where we're going to go next. Do you remember what the reciprocal of sine is? Remember what we called that? Yep. Sine is 1 over cosecant. So I'm actually going to do 1 over sine equals cosecant. Good. No co, co. That's how you remember. Co and no co. Now this is an identity too. This is always the same. It's always true for any value of theta. What's another one? 1 over cos is, what was that? There's a co there, so no co. Remember this? Cosecant theta. And finally, 1 over tan theta is cotan theta. These are the reciprocal identities. Those are always true all the time. And you know about those from before. But they are now, we can call them identities. Always true all the time. Now I just want to say one thing here. Of course, there is an equal sign. Okay, there's an equal sign in all of these identities stating that one side is equal to the other side all the time. So that's very true. However, in this chapter, as we move through, one of the big things that you're going to have to remember is that this is not an equation that you can manipulate like other equations. Okay? We cannot multiply both sides of an identity together and treat them as equal. Okay? We cannot treat them as equal to manipulate them like we can other expressions, other equations. Okay? It's very different. And I'll tell you more about that. I'll explain more about as we move through the chapter. But these are equals, but they're different than equations, okay? So, and it's a bit of a touchy thing, but you'll find out more about that as we move through. All right, so because of those reciprocal identities, we have several forms of the Pythagorean identity. So let me just talk about that for a second. We know that sine squared theta plus cos squared theta equals 1. We know that. Now, if I did this, expressed each of these as, or if I divided both sides of this identity, okay, I am treating it as an equation right now, but I'm just showing you how I would get different forms of these. I'm integrating both the reciprocal identities and the Pythagorean identity, okay? If I wrote these as this quantity over sine squared theta, all of them, okay, because this is an identity, I'm going to do the same thing to everything. What happens? I get a 1 here. Over here I get 1 over sine is cosecant squared theta. What's cos squared theta over sine squared theta? You know what that is? Yes, it is. It's cotan. So cotan squared theta. Okay? Because we can manipulate the Pythagorean identities, because they are always true all the time, I'm just writing each individual term that's consistent with itself using the reciprocal identities. You can rewrite the forms of the Pythagorean identity. So that is another one that is true all the time. Okay? Now, if I did this, I'm going to change dividing by sine. I'm going to change that to dividing by cos. Okay, so if I did cos squared theta, cos squared theta, and cos squared theta, what would I get? I would get sine over cos is tan squared theta plus 1 equals secant squared theta, and that is also an identity there that you can always take to the bank. And because it is an identity, and we're not solving this equation, okay, you can move things around here as well. That this is okay. But solving equations and expressing identities, I just want you to know, are a little bit different thing. But we can move the terms around here, and you'll see different things happening in your textbook there. You'll be able to move these things around. But those are the identities that come from the Pythagorean identity. And maybe just to clarify, yes, tan theta is sine theta divided by cos theta. So that is, I think that your textbook might include that as one of the reciprocal. Oh no, it's a quotient identity. Thank you. Quotient identity. I see that now. Oh, that's what I have next. Oh, awesome. Okay. Yeah. Started these notes yesterday. There you go. So let's bring that down here. That's one of the quotient identities. Yay. So a trig function that can be written as a quotient. And of course, the other one is the cotan theta. And you were right to say before that that's cos over sine. All right? Okay, so as we summarize here, there's a few other points I need to make just for this initial section. And an identity, okay, right here is always true, okay? It's an equation involving trigonometric functions that are true for all possible values of the variable. I want to focus on this, all possible, or permissible, I guess it says, permissible values of the variable. If we go back to what we just talked about here, okay? When cos of theta is 0, so for like pi over 2, 90 degrees, this does not hold true. Okay, that's not going to work. It's not a permissible value for this. So we wouldn't be able to use this identity in simplifying anything. Okay, so you know what I mean? So that's tan is undefined at pi over 2. So you can see why it is, but there are non-permissible values for some of these identities. Okay, and that's an example of one. Okay, let's see what this will say. You can verify trig identities numerically by substituting values, which we did. Oh, graphing using technology. Okay, that's an interesting one too. If we graph one side of the equation and the other, they will be the exact same graphs for any value of x, any part of the domain. That's how you can verify graphically. So if I type this in, which let's do that real quick here. All right, so I've graphed cos squared x plus sine squared x, and I've also graphed y equals 1. And as you see, there's two graphs coming up there, but they look exactly the same, don't they? So there's that one, okay? And there's the point there, 0, 1. And if I go to the other graph, 0, 1, same point. So the graphs are the same. That's how you can verify graphically if something is an identity. Okay? So I want to try this, actually. What if we did the one we did before, like square root of x, and then we squared that. Let's see. Insert bracket there. Bracket squared. And just x. Interesting. Let's see what happens there. Oh, look at that. See, they're not the exact same because I don't know if you caught that, but the first one started at 0 and went on up like that. And so, and y equals x includes the negatives as well. So you were right to say that, hey, it doesn't work for negative values. That's not true for negative values. So you are very correct. It's the same for all positive values, but it's not an identity because they're not exactly the same at all. Okay, got it? Everyone on board there? Okay. Okay, so here you go. Verifying two sides of an equation equal for all given values that appear to be graphed. Is still not sufficient to conclude, but at least it gives you an identity that you can verify as much as possible, okay? But we are going to work this chapter on proving identities. So I'm going to show you how to do that, proving statements. Okay, so that's the intro to the chapter. I know it's a kind of a long identity lesson there, but yeah, if you pay attention to these, I'm going to give you some questions from the textbook that will allow you to kind of explore these relationships. Manipulate means to kind of reorganize or to rewrite in a different way.